Hello everyone, we are back with our coding session, and now we will code what we have derived in this equation of theories, the inverse kinematics and some kind of P controllers. Before doing this, I have just created a classical gazebo map, and now we will just open up a Python script, which you can just go and say touch YouTube motion .py and ls sudo chmod +x YouTube motion .py. Just enter your password, and if it's green, then it's authorized. Now we can just go, and I'm just suggesting using Visual Cut for beginners of the ROS environment. And before everything, you just have to do this: user binary environment Python 3. This is your basic compiler, which you shouldn't forget. And first thing first, we will of course import ROS/Py. And now let's just go and import when it's necessary. First of all, let's define our class. Let's just say this is robot. This is just an object, and we can call def. Normally the copilot is better for this, but unfortunately I just lost it. I just lost my license. I just used the free extension. And now let's just save it. ROS/Py.init.node. What should we say? Motion planner. Anonymous should be equal to true. And now, first of all, let's just assume, what do we need? We need a velocity, we need odom, and some kind of placeholders. Let's just starting with publishers, self dot velocity publisher should be equal to ROS/Py dot publisher, which we will just connect to cmdvel. Normally just every robot use cmdvel, so just be okay with it. And we will say twist, and I should import twist. Query size should be equal to 10, and from geometry, this is just a basic geometry.message.msg import twists. If I'm not mistaken, this should be the one. And okay, we have our publisher, which will just publish the velocity. And now what do we need? We need to find out where we are. Where can we find out if we are not using the localization just for now? Odom. We will just subscribe to the odom. Let's just say subscriber. Okay. Self.odom subscriber is equal to ROS/Py dot subscriber odom, which is just Odometry, which we will import just a second. Self dot, let's just say odom callback, which we will just write a callback function for this to continuous derivation. And from navigation msg he will import odometry. And okay, we will have subscriber, we will have publisher, and let's just go. And first of all, let's just finish the init part for now. We will just apply it when we see necessary things. Let's go. Well, first of all, def odom. I just get used to that GitHub couplet too much, which will just self and data, which will be inputted from our ROS system. And first of all, we need to extract extract position from our odom data, which is self dot current position. We didn't write current position 0 should be our x data dot pos dot position dot x, and similarly our y should be equal to this. And now we will just use quaternion. And by the way, you may just believe that I'm making a magic, but this is just a basic odom callback, which is generally used, so I just kind of get used to that, and I remember it like my name. Quaternion should be equal to data dot pos dot orientation dot x, comma data. Just give me this. I'm so lazy for this. And just write it for 4 times. What was this? This is not x. This should be y, this should be zeta, this should be omega, and if you're working in the space, we will not need this, and this should, your zeta should probably be equal to 0, but just write it. And now we will just try to convert quaternions to Euler angles. Euler, let's just say it, is equal to, we don't know, we don't have TF that transformation. I'm just gonna write it, transformation dot Euler from quaternion, lovely name, quaternion, which we will have self dot current position second should be equal to Euler that 2. So you can just think of it as yaw angle. You can write it like this, yaw angle. Sorry for this. So we have x, y, and theta, or yaw, as you may call. For now, we will just import tf dot tg. What the heck is tg? Transformations. So for now, we will we have odom callback, and now what do we need? We can just put a placeholder for this, like self dot, let me just say initialization self dot current position. Let's just say 0 0 0 for initial, which just represents x, y, and theta. We will just get this from odom method, but just for now, for a placeholder, we can just go on. And after that, what do we need? Basically, we need after we need our inverse kinematics, but for some reason we have some way of putting our wheel velocities. So let's just go with this, adding our def set left wheel velocity, which we will just give self and velocity. Sorry, velocity. Oops. In radian velocity, but let's just say in rad. Let me just write it fully in rad over seconds. Rad per seconds. So we will just give it. And what do we have? We will just say velocity. Why I cannot write it right now? Velocity message should be equal to twist. And after that self, that's, let's say, left wheel velocity from here. Where did you find it? Oh, sorry. Self dot left wheel velocity, not that one. Left wheel velocity should be equal to velocity in radian per second. Fine with it. And I forgot to that, sorry. After that, we will just go in with velocity message dot linear dot x should be equal to 0.033, which is the distance, the radius of our tire in meters, which we will have self dot left wheel velocity plus self dot right wheel velocity. Let's just say right wheel for now. I will just add on velocity, and this is over 2 as we have right, and our velocity. And I guess we can just go on with just say this is all. Like, do we need it? I'm just curious, do we really need to write the left and right wheel? I'm not sure, but let's just write it. Sorry again. Velocity message dot angular dot zeta is equal to, let me just take it, be a little bit lazy for now, which we will just probably subscript this from here, and we will just say over 0.60, and we will just say self dot velocity publisher dot publish velocity message. So that's it. We can just write it again. Let's just make it like this. They are basically the same things, but I can just write it. It is easier for, let's just say right, and let's just say right, and this is okay. Nothing changed. By the way, 0.160 is distance between the tires. And after this, we will come out with how do we, with our velocities, def set velocities function, which we will have self linear velocity and angular velocity. Boom. And then first of all we will calculate the wheel velocities in radian per second. And let's just say I can't write just the fancy sample, so we left should be equal to linear velocity minus angular velocity minus self that robot radius, which I will just give in the initialization parts. I forgot it, sorry. Radius. It was around 0.33 probably. Or self that wheel radius. Let's just say I just don't want to use the 0.60. It's more hard coded. I like it that way. So the left, and this is just say we right. Oops. But this time this just have plus. Oops. And now these are all the same, and we will just publish the velocities, and we can just say self.set left wheel velocity as v left, and we will just self.set right wheel velocity. Something is happening. We right. What the heck I done? And this is we right. Sorry for a little bit typos. And let's just, before we go into the motion control, let's first write the initialization parts. So let me write it from self.wheel radius, which should be equal to 0.33 in meters. By the way, I am not making these up. It's all TurtleBot. Self dot let's just say robot radius is equal to 0.160. Normally I was just going to hardcode, but this way it will be probably better. And for the initialization, let's just say self wheel velocity. For now, just say 0 right wheel velocity, or just, I'm not sure, I didn't get an error, but let's just see if something happens. If something not, we are okay. And now our final part, feedback control. Our ugly piece, def feedback control parts, which we will just input self, and we need to draw. What do we have? We have the current position, which basically a start position, and we should have a final position so that we can just calculate these ugly equations. Well, let's just say this is final. I will define later. And for current position x, y, and theta, which is just represents orientation. Current x, comma current y, comma current theta should come from our beloved self.current position. Okay, I write it so ugly position. Probably I just made a little bit position typo here. My keyboard is dying probably from lots of writing. And what's our target? Our target position, which is our also the goal position. We can just say the same things. Target x, target y, and target theta should come from final, which we will give in probably the while loop at the end of it. First of all, we will calculate angle to the targets. Like, just assume, first of all, we need to just turn for some kind of radians. In order, if we just move and try to curve, we will just draw a little really big circle, which we probably will hit something else. So angle to target angle to target, which we can say mat, that's a10, and we will just import mat function target. I just made a little bit typo again. Where is my mind? Target y minus current y. Comma target x minus current x, which, because this will be basically a loop, and just mat for sake of it. I just don't like that yellow. Probably just doing it in the end would be better, but this isn't for now. This is better, and we can just find out the angle difference is equal to angle to target minus current theta. And I don't like this. I just love a little bit blank here. It's better for visual or readability. Okay. So what do we have now? And we need to normalize this for using our I1. Normalize the angle difference. You can just say angle difference is equal to angle difference plus mat, that's pi, and just say percent or 2 times mat, that's pi, just basically the normalization equation, minus mat pi. And now after this we can just calculate, what the heck is going on? We can just calculate the distance to targets from here, and let's just say distance to targets. I really miss my old things, especially the GitHub Copilot, which is just made for this kind of operations. It's boring things. And let's just say target x. How do we do it? Target x minus current x, and just say square root plus a little another one, target y minus current y square root, which we will just say the square root, and we will have the row, which is basically, let's just say row. This is not p, but you know from the other lesson, this is just the row, classical from the Greeks. And after that we will find out the angle difference, distance to target, and now we will just have the control gains for our final set. Control gains, which we will have angular gain. This is just k alpha. Let's just say 1. I have tried it and 1 is better, linear gain, but we can just always play with it. Linear gain. And let's just say this is 0.5 for decreasing this impulsiveness. And before we go on, I just want to define something. First of all, the maximum velocities. Every car, every mobile robot have some kind of limits. And this TurtleBot has maximum linear velocity. Maximum linear velocity, which is equal to 0.22 meter per second. Also maximum angular velocity of 2.84 radian per second. You can just find it from internet, so no problem for me. But I'm doing this, but you will see, even if these are the max, in real life you will probably just get the quaternion of it, just a quarter of it, because the robot will be too fast and it will slip, and we don't want this. And before we go on, we need to initialize this linear velocity initialization from here. Initialization. Let me write it. Initialization. I just write it wrong, but you get the point. Linear velocity is equal to 0 at the beginning, and angular velocity also equal to 0 at the beginning. And for now, before we go in, let's just assume this. First of all, I want my robot to, as the thing I mentioned earlier, first of all rotate and just be in the same line with the goal, especially if we are not using some kind of angular A-star algorithm. First of all, I want them to be on the same plane. Theta and alpha should be 0. So we will rotate it. Rotate first to permit really large circle of movement. I don't want it to go there and then rotate, so we will just say if angle difference, let's say bigger than 0.05, which we will just define a threshold, we can just say this: angular velocity is equal to angular gain times angle difference. So it's just like a basic KP, and we can just say, in order to get this maximum velocity limitation, angular velocity is equal to maximum and also the minimum of angular velocity and maximum angular velocity. We will get the minimum of it, and minus maximum angular velocity. This way we will, for sure, we will make sure that we are in the safe position. LF distance to target, like if there's nothing happened, let me just say it, rotation has been finished. Just go forward. Distance to target, let's say bigger than, 0.1. Just be careful with this. If it's too small, probably there will be a little bit problem. The robot will be so close, but it's a little bit hard to do it. Linear velocity is equal to linear gain times distance to target. And okay, after that we will just do the same magic that we have done to that: maximum, minimum, another parentheses, linear velocity, and say maximum linear velocity and minus maximum linear velocity. Sorry, something happened. Yes. And after this, if there's nothing else, just print out, print goal reach. Goal reach. Wahoo! Wahoo! So this is our basically the thing, but the problem is we need to publish this, okay? Publish these. Why the heck I cannot write it? Publish these velocities. Self dot set velocities linear velocity or angular velocity. So this way you can just define a certain threshold, but I don't say anything. So probably we just define all of it. We have angle difference, we have all of it, and this is, we'll just say set velocities, which will calculate the inverse here, and it will separately just say we left, we right, and this is our Odom callback for knowing, let's just say, for knowing where we are, and after some time, knowing where we are, after some time we will use AMCL and UKF as I mentioned in my previous video. But for now it's perfectly enough for us. And let's just say this. Let's make if name is equal to main. I hate these symbols. Equal to main. And using too much MATLAB burn you down. Let's just try it. First of all, just for your instance, I'm suggesting using this, especially in trial error. ROS by that, wait for service, Gazebo reset simulation. By the way, I write it wrong. Reset simulation, this should be has some kind of underscore probably. And reset model SRE for just resetting in every try. We will use ROS dot service proxy Gazebo reset simulation, and we will just call it empty. Should we really write it? I'm not sure about it. I'm not sure. Let's just don't write it for now. I don't like it. Just waiting is enough. And for now, robot instance is equal to our robot. What was our class name? I forgot it. Yes, robot. It's smaller. Robot. Okay. And then we can just say final position. And from the map I will show you later, we can just say this is 2.59, let's assume 0.7 say, and minus, let's just say 0. This is our final position, and especially our domain loop while not ROS. This is basically the best ROS command I have ever solved. Is shut down unless I say something else. Just try to do this. Robot instance dot feedback control final position. You are just going to give me the final position. I'm just going to give you and print for debugging reason. Just think of it. We need to find out where we are. And let's say from here current pos. And robot instance dot current position. We are updating it, so probably we'll know it. And we have to ROS dot sleep. Would be better. And we will sleep for like 0.1. It's perfectly fine number. And accept ROS dot ROS interception. Sorry. ROS interrupt. Wasn't it like this? Wait, I missed it. I remember it's like this. Is it because of it? Except ROS by dot. Okay. Idiot ROS. I forgot it. And we can just say interrupt exception and say ROS by dot login for our debugging purposes. We have arrived. And for fantasies, we can just say ROS by dot signal. My lovely command signal shutdown. That's our code. So it's not the hardest one, but not the easiest one for sure. And for now, let's just say, let's define our current position. These are the values from Odom. So for now, I'm just going to write it for like this, 3.59. I just get it from the Odom. And this is 0.40. And let's just say this is 0.0. And for now, before we just run this, we will just say cd and we will just make a cat can make. I hope nothing happens. It has been a while. Yes. And normally, probably yours should be faster because I had a lot of project going on. And for now, let's just open map, mobile robots, mobile world, launch. Just wait for it. And this is our robot. And for now, we can just say ROS-topic echo Odom and 1, and you can see this. It's minus 3.59. Sorry, 3.59, 0.40. Yes, as I mentioned. And now we will say ROS run mobile robots YouTube motion.py. And for now, what did we give in the final position? We just gave 2.59 to 0.7, and we can say 1 to 59 0.7. It should come to near here. If probably, unless it hits something, it will just exit it. Luckily. And wait, we had something. Oh, what the heck is this? I got an error. Import TF transformation. What did I made wrong? Where does it say this? Line 37. Float object is not callable. Let's say Euler TF dot transformation dot Euler from quaternion. I got an error. I don't know why. No idea. Hello guys, welcome back. I just am kind of make debugging. First things first, this should be, of course, multiplication. Somehow I just write minus, and this is 0.033 multiplication. I forgot to mark multiplication mark, and this should be the parentheses. And transformations.s, it should be s, not transformation. I forgot the s, and now we are good to go. This is our map. This is our, for now, yes, you may see this robot has just go there. And probably it will reach, yes, it has reached, wahoo! And if we say this, we will see we have arrived. ROS Py signal shutdown. If you like, please give me a like and please subscribe. Thank you for watching.